So, welcome again, everyone. Today I want to continue Markov chains, but in a different path. Last week I told you mainly about the common way of talking about Markov chain, which is in terms of dynamical systems, and then I showed you different stuff like different properties or steady-state properties, and then this kind of ergodicity and this kind of factors like K-many constants and properties of Markov chain. And then if you remember, I showed you these applications that for some of you might be interesting, for some not. So this application economy or transportations and yeah, this kind of thing. The second approach, and I think this would make Markov more happy, I would say, is this one what I'm talking to today. So this is about this is not about dynamical systems any longer. It's about encapsulations of complexity in a way, and I will talk about this in terms of representation, and then in principle how we can represent objects, and these objects are abstract things that we can realize them in our data set. So I will start, and I will talk mainly about natural language processes and natural language models, and then at the end I will show you in principle this approach is so generic. So what I'm going to talk is just to tell you a certain story about Markov as a pioneering work in this field, which is called relational representation, and then next I will show you other applications which are inspired by the idea. And usually the problem is that the reason I'm starting with this is that in the literature of machine learning, people don't refer to Markov. People refer to later works like in 1960s or 1970s if they're really caring about the literature. But I think what Markov did in terms of natural language modeling is really unique, and is, I would say, the first one. So before that, I will just continue a bit what we did last week in terms of using Markov as a kind of generative tools. I already told you that this is not a good thing to use Markov chain for generating, but since it was the original example of Markov in the real natural language or text, I will just show in this application. In this case, this is a data set that we are going to use today several times. This is a known data set called sentiment data. These are a collection of movie reviews from IMDb, and then we have a lot of them, and they're all labeled either positive or negative. So somebody has read them and then said this is positive, this is negative. We are going to use this data later, but for now we are just going to see how we can implement a Markov chain on this language. So this was in principle his original idea, but that time it was not possible. But now for us it's like this, because now we have the computer, right? So imagine now we have 225,000 texts only on positive, which is okay for now. And then each review is, for example, like this one. Bromwell High is a cartoon comedy, and then it's a kind of description. So what I'm going to do is that first starting building a Markov chain at the character level. And what we are going to do is that we just simply take the letters and space and remove all the others, which is not a good thing in principle, but just for simplicity. So I wrote this function clean text, and then I just clean it. So I remove them, and then I go to line by line, and then I replace this text to these kind of things. Now you have Bromwell underline, which means space, high is right. So now think about it like what we had as a random walk last week, you remember, right? The guy was going left and right, and then we created this state, which was the number of accumulated number, and then we are reading this like possible state as possible state. Now our states are in principle 27s, right? Because we have this and then 26 letters. So we have a very simple Markov chain. So it's just for fun, and later in the recurrent neural networks you will see that how recurrent neural networks are beating Markov chains in this term because of the notion of memory. So I simply make this, I call it nchar, which is the Markov chain of characters, and then you have it. And so as we did before, now we can simply check what is the most frequent letter or characters or state in this text, and which is this one. And this might be a valuable result, I don't know, in Russian or English, maybe, I don't know, more than 100 years ago, to know which word is like the most frequent word, or which letter is the most frequent, and then just building it on top based on this Markov chain idea. And then if you just visualize this, you will see that this is the Markov chain, and then each row in principle shows you the transition probabilities, right? And if you can condition that in each row, then for example you can select U, and then it tells you what is the probability of the next characters after U, right? So just think about it now as a kind of generative model, which means that it has a Markov property, as we discussed last week, which has no more than no long-term memory. It just looks at what you are and then what's the next steps. So if you think about it as a generative model, it's a very weak model because it has no clue about the context. So this is as we discussed, this is the wrong way of using Markov chain, but we are going to show it what happens at the end, and then this will be the starting point for the interesting part. So now if I just train this, I have this Markov chain. You can think about this as a kind of extraction of this language or this set of text, and now I can start with a random initial characters and be greedy. So it means that if I am at the row of H, I see which one is the most probable one, and then I just take one. For example, if I generate H, I say next would be E. And if you do that, independent of the initial condition, it always ends up with this kind of patterns. You see, yeah, like let's change it. It's a WAN and then space, and then you have this this recursive pattern, because you get trapped in a loop, right? Because you are greedy. So it's useless in principle in terms of generative part. But let's take a probabilistic pattern and then choose the next character based on the weighted probability. So the one which has higher probability is more likely to get it, but it's not absolute. So if you do that, is this one. Again, is simply useless. But still you have these kind of patterns which are hampered. So what is happening is that in principle we see simply it doesn't work. So this is not a cool idea to implement. But if we now go to word level, we can as you will see that we can get a much better result. So for this part there is a problem, because now the number of words in a small corpus of document, it goes it increases drastically. For example, if you have a few 25,000 texts, short text, you most likely you will get around 20,000 unique words. So your status space is 20,000 by 20,000. And then now we are going to do it at the level of words, because characters level is not helpful. But at least we just assume that now we have these words which are kind of clusters of sequences of the characters, right? But then another option that we have is not to look at one step. We can look at several steps. But then we don't have this transition matrix. We should keep them in this in like a decision tree, right? You just say hello is one word, and after that this word, this word, this word. So from each word, next word, if you have second order Markov chain, you need to keep 2 steps. If you have third order, and so on. But there's a problem. The problem is that you have a status space explosion and then data storage problem, right? But nevertheless, there is a nice implementation with Python called Markov text that I already did this, and then you can do it as well. Just change the depth. Like when it's depth 2, means that you have the first order Markov chain, and if it's more than that, it's like 2 steps. And I already did this, but it takes time. But now you can generate codes, and simply it stores the data in a database in a kind of probabilistic trees, and then it iterates over these trees, right? And now if I use, let's say, 2 generative, yeah, it's generative, right? So I'm generating just random things. So it generates something which looks like a text. It's really good, look like something for it. But then if I increase the depth, it will get better. For example, now it says I had to be caught in laughter when he first appeared. And you see, it's like almost generating the same thing. And actually there is no AI here, and it's a very good thing to use for fake news. And recently there was like one thing in Twitter was everywhere around, is very viral. And actually you can generate random text like this, which looks like a thing, like a real thing, but it's not. And if you increase the depth, in principle what happens is that you can simply regenerate the text. You cannot. So in principle, now what is interesting is that this simple structure is encapsulating all the complexities in it with this very simple setup of matrix, right? But at the same time, the problem is that it cannot generate new things, and this is always the problem, because as a person we can write sometimes new things. Of course it's questionable, is it new or you're copying something or not, but in principle this is not possible here. So as we discussed last week with another example with this random walks, I think is not a good idea to use this kind of Markov chains or similar things to generate new things. And actually this is a fundamental problem at the moment in machine learning as well, how to generate things. For example, it's easy to translate one language from another, from German to English, but it's not possible to write something in German. Or it's not possible, for example, to generate a picture easily, right? But it's easy to say if you have a picture, if there is a cat in the picture, or if you want to use it for self-driving cars, because you are not going to generate a picture, you are just going to use it. And this is the problem of computer vision. So these are really powerful, but for generating, no. But it's fun to just play with that, and just don't think about it that it's just for text. You can think about anything as if you have this status space, then you can generate things. For example, you can generate arbitrary floor plans if you have labeled, semantically labeled elements in a graph. So you can parse this graph and then later generate this text. So this text means that you are generating these random graphs, and if you can connect them together, this can be somehow randomized floor plans or anything. Or if you have molecules, or if you have a lot of compounds and so on, you have these symbols, and then you can generate these things by just going through random walks over it. So what you should be careful is that when you have a larger data set and then more agglomeration, aggregation and more depth, usually you have this problem of a status space explosion. So a very quick conclusion on this part is, as it can be seen, the generated results are far from being reasonable. They're just mimicking the data, and I would say they're good, but by the way they're really good for generating fake news. Yes. And it's easy. You just feed a lot of text and then you generate a lot of speech. No? You can do it. Yeah. The second part, which is interesting, is about representation. Now we think that anyway this mathematical concept of Markov has some interesting property, which is it's able to encapsulate all of these probabilistic sequences. Because if you think about each text as like random or some meaningful sequences of the symbols, now with this simple matrix you have these encapsulations in this kind of probabilistic relationship. So what I want to say is that this will introduce a new types of representation, and this is what we call relational representation. Before that, I think it's good to know what are the typical way of representing objects, and I call it you can call it a rational representation of the object. That usually this is our data set. Usually you have a matrix. These are your rows or your objects, and then you usually have a set of features, and these features are a priori selected. For example, you want to compare these houses for the prices, and then you have these elements of the house, like number of rooms, size of the house, and then age, the construction company, and whatever, and then you have some at the end, for example, what is the price of this house, right? So you have these columns, which are the features, and then you have these rows. What implies here is, and this is, I would say, this is the modern representation of the data, that you have the notion of generic object. You assume what is a generic house, and then you say a generic house has these properties, and now any property, any concrete property is an instance of this generic or abstract class. And then at the same time, this is sometimes called a model based on abstract universals, because you have this notion of universality of houseness, for example, with this abstract definition. And it's almost at the same time, you can say it's related to set theoretical definitions of models, but these are different things. So what happens here is that this is usually you have. But think about it now for text. Now you have words in this language, how you want to represent them in this kind of a priori setups. Usually it doesn't work like that, because you can say, okay, the rows or connections to the other words based on given dictionaries, and usually for this kind of complex problems we don't have these data sets. And at the same time, for the other data sets that we usually deal with this kind of representation, these features might be arbitrary, and then sometimes you just say, I just chose these 5 factors because it was what I had, but you don't know is it the full representation of the thing or not. So because you reduce the objects to these few parameters. And if we have few features, the space becomes small with the size of the data. So if you have like 5 factors, and then if you have millions of records, you cannot use this data because the space is already filled, right? And if you have a lot of factors, and this is the problem, for example, in a lot of engineering problems, if you have a lot of factors, the experiments are expensive, because the combination of these factors, the combination of all of these factors is really exponential. So we have another kind of presentation which is interesting and is not opposite, it's a kind of alternative to that, is when you have this kind of network-based representation in your data, that you are connecting concrete objects now to each other. What is important, I forgot to say here, is that here you always assume that you have independence of observation. So, and it has a lot to do, I mean, if you want to classical Newtonian mechanics, that you can assume that there is an independent observation, you have independent, for example, you can think about even in particle physics that you have these particles as independent elements, idealized elements. So this kind of idealization, it has a long history. But what happens is that in a lot of things, as you will see, you don't have this independence any longer, like the text or meaning of language, for example. So just to create a symmetry, I would say here we have the notion of independence of observation, which is a very important notion. I think started, I would say, by Descartes, I would say. And then you have this kind of classical notion of measurement systems and so on, that you assume that you can measure this observation independently. We have these IID observations as well in statistics. And then it fits very well with the rule-based or mechanical societies or setup, that you know the rules, and then by that you generate these objects. So you can say, I look at all the people in the country based on these 5 factors. So in principle you don't care about individuals, you just care about the parameters, right? So you look at the people through these parameters. The other way would be to look at the relationship between these objects. So in principle, this is when you have representation that I call object-based representation. That now you say A is a concrete object, would be like one person, like a real person, or one word, or one element. You just say A is the negation of all the others, and then B is the negation of all the others. So you just introduce a new kind of representation, which is by negating all the others of that concrete elements. So what happens is that you create this kind of self-referential setup, and this is nowadays we have it a lot in a lot of things, like in Markov chain you have this setup, in web you have this, in friendship relation you have this, and this is very obvious for recommendation systems. Sometimes they don't look at what is the content of this book, but what they say is that if this person has read this book, and then you have read this book and you are friend, you're most likely you're going to read this book. So this is a kind of object-based representation, and what is helping here is that we don't need these a priori definitions of the model any longer. But the problem at the same time is that it's pure data driven. Like if you don't have data, you cannot do that. Whereas for the previous one, you could simulate synthetic data, right? This data could be not real. But always in this case, in the case of relational representation, you need observed data. And this is because of that you say the universality is concrete, is not abstract. So what we have here is that we don't have any longer independence in observations, because if I have a feeling about A, this will affect all the others, right? So in principle, your definition of any of these concrete objects will affect the others. So if you have a word, if you have a meaning, a certain understanding or impression for a certain book or word, for example, in the language, it will affect the other, your impression from the other books or other words or any other people in any kind of setup like that. And it's very generic and it's very powerful as well. And then if you think about it, this is in principle what Markov claims here, because he creates these relational setups and then this is a body to represent the objects. So I would say this is another not common way of talking about Markov chain, and he had this idea how to encapsulate this complexity, but not necessarily to generate things, but to encapsulate the thing. And then Shannon as well mentioned this in 1948, and he was in 1906 or 7, and then didn't work because there were no data, no computation. And gradually we had more data and more computational power, and I think the first prominent application of this idea was Google PageRank algorithms, because there as well they have the connectivity of the net, and they were able to sort the pages based on only connectivity to all the other pages. And actually they as I told you last week, they convert the this internet network to a Markov chain, and then they calculate the first eigenvector steady state, which is the PageRank. So, so the question is that now, what is this good for in principle? As you will see that this is extremely helpful, and it will reduce a lot of problems that we had. For example, like status space exploration and representation, and then in I think if you go to natural language processing or linguistic, for example, we have this historical works like and references. This is a very nice I think presentation. I don't remember presentation or paper. And then you have references to Harris, is the known person in this field, and this in linguistics sometimes this is called distributed semantic models. And the opposite school of thinking in this linguistic is first you need to build a model of the language, and then you can produce. And then the question is that you're always in a catch-up process because you don't know what is the model of the language. And then the other side of the other camp is to just say we need to have a lot of data, and then we can encapsulate whatever is the model. And that's a beautiful thing here. In principle, all of this relation could be based on any of these features, but since they are emerging out of data, you don't know, and you don't want to know why. For example, you don't know why these two, for example, this is fully connected, which is not a good example, but in principle, these networks are not fully connected. For example, if it's about road networks and they're based on the flow of cars, there is a reason why they're going from this region to this region, but you don't need to know why. You just have it in your data, and then this matrix is encapsulating all of them together. Whereas if you want to have this kind of approach, which is similar to, again, to this having these semantic models, in traffic, again, you need to know why people are driving from this area to the other area. So you need to know a lot of activity rules, and then you need to hard code this in your data set. That's the beautiful thing. Now, if you have a lot of data from mobile phone traces or GPS traces and so on, you can build this nice data-driven simulation. Or if you have a lot of text from spoken language, you can encapsulate all the possible rules of, for example, English or something like that. So, but you don't know what are the rules. And this is, if you remember in the first session, this was all about this. Forget about knowing why or how, because you're just encapsulating everything in that. That's the whole idea. So if you think about this as a generic framework, there are many applications. For example, think about a pixel in an image and their neighboring cells. They're all telling the same story, so you have always contextual information. You can think about that as an image as a two-dimensional Markov environment. So you have this kind of Markov properties that you can say, if I only know the label of my neighboring pixels, I'm safe, right? then you assume that there's this kind of a spatial correlation. You can think about this like these conditional probabilities that we had here, that if you are at H, it's more likely that you will have similar things that you have in E. So you can think about as pixels as like that as well. But this is then it's called a random field, for example. Then you have not a chain, you have a field, and then, for example, you have the notion of Markov random fields, for example. So, or another thing, a house and its neighborhood, for example, where one would be the example I told you, that you say this house has this size, this type, and this element, or the other one would be to look at all the other neighboring house. So sometimes you don't need to specify what is inside, and that's the problem, for example, with big data nowadays, because sometimes you don't need to say, you anonymize your data, but by knowing all the other data around this data point, you can say who is this person. But you don't need to know exactly the name, or so this kind of problems now we have with this big data and this kind of network data in principle. And then a person and his friends, a combination of different elements in a floor plans or building systems, they're all possible. Or combination of different elements in a chemical compounds. So you can think about all of them as a kind of probabilistic structures, right? Or think about as an ingredient in a food recipe, for example. Now you can make, I think I've seen applications like mobile apps for that you can say, okay, I have this kind of material, or this kind of fruits, or this kind of basic material at my fridge. What can I do, for example? So this kind of network can tell you, in principle, based on reading all of these recipes of foods, I can tell you if you have this and this might be a good fit, for example. This is a kind of recommendation system. But it's just based on the data, and it has no clue about what is food, what is recipe, and so on. It just finds this correlation in a meaningful way. So what is I'm repeating several times is the notion of co-occurrence, or happening things that are happening together. This is the information that now we are using for representation, as you can see here. This is you can think about this as a network of co-occurrences. So, but as you will see, let me find what I was saying. Okay. Now, if we take, now, as I said, now we can think about it as a kind of representation, right? So if we have a lot of characters, for each character I have a representation. Without knowing what is this character or defining it, I can say, I just look at the corresponding row, or even I can look at the corresponding columns and put them together, and then use this as a kind of representation. And I do it here. And then now I have it 27 characters, and then 27 dimensional data, and then I can train a self-organizing map for fun, or any other methods, and then you will see that if you map them, it will be like this. So there should be some meaningful patterns here, like this O, A, I, E, they're all together. This means that they have some similarities. But as I told you, I don't trust to this. I will show you a better example, which is based on Word, and you will see that how powerful is this concept. So in principle, if you are interested to have a map, here it shows you that this concept, it works. And it's important if you have more data. If you increase the size of the data, it gets always better. So now we are doing the same. Now we train this, we constructed this Markov character-based Markov chain, and I simply take one row and then train a self-organizing map. As you see, it has some meaningful pattern, right? So, but what is the problem here is that you might say it's not just enough to look at one word. So in principle, we can look at a lot of words. And there, the problem we will have is, in principle, is a status space explosion. And just to quickly mention to some other methods, is that in principle you can make this kind of co-occurrences matrices, and this co-occurrence matrix would be in totally different way. If you go to a standard NLP library, they have a lot of this, byproducts of this co-occurrences matrix, and then you can implement, for example, PCA, or as I did, like SOM, and then a lot of probabilistic versions of PCA, and they have different names like LSA, LDA, SVD, which is the method for that, and then PCA. But what is the problem they always have is the scale and the speed of and the memory that you need. And another problem is that if you add more relationalities, the dimensionalities increases. And then there's a, maybe I should tell you that there's a technical problem, that if you have, for example, 20 observations and then you have like 200,000 dimensionality, usually don't get good results, because in this 200,000 dimensional, or let's say 2,000 dimensional space, they're completely separated. So we need to find a way to dense them back. So that's the problem with Markov as well. This matrix, as you see here, is very sparse. So you need to somehow compress it. And this is what you do with all of these methods, like PCA or the corresponding methods like latent semantic analysis or LDA or something like that. So this was like before 2010, and then after 2010 there was a nice idea that you can, and this is called neural embeddings, and this is a game changer idea, which says you don't need to build the co-occurrences matrices, because what we did, like in the SOM or the PCA or all the other methods, they first build this large matrix and then try to compress it to, let's say, to 200 dimensional vector. But then this guy, they simply said we don't need to build this co-occurrence matrix. You just need to train a classifier. Let me read it from here, maybe it's better because otherwise it's confusing. Instead, learn a classifier that predicts a word given a context around the word or the other way around. So in principle, what is happening here is that you just say, I train a classifier. This classifier, think about it as a generic model or a kind of neural network, that you look at all these words around these words, and then you should say, like, I look at 2 steps before, 2 steps after, and then the classifier should tell me what was the word. And it looks a bit stupid because it's a kind of unsupervised problem. You don't construct this matrix any longer. You just try to predict what's the missing word, or the other way around. You just say, if I have this word, what was the words around this? What's happening is that we are doing some kind of encoding here. And this encoding is, if you remember, it's similar to this PCA, but PCA was linear. We are doing it in a non-linear way. And then, to just make it short, because I don't want to go to the details now, you train a network with this one layer, just one layer, and this layer, for example, is 100 dimension. And these arrows, in principle, are matrices, like matrices, just one matrix. So the way you represent this is called one-hot encoding, which is a usual way. So for example, if you have 2,000 words, unique words, you need to have a 2,000 dimensional vector, which has everything 0 except 1. For example, if hello is the first word in your dictionary, you just say hello is 1, the rest is 0. The next word is, for example, manos. For example, is 0, 1, the rest is 0. Right? So this is called one-hot encoding. And you just feed it by this one-hot encoding. And imagine if you have a large database, this one-hot encoding simply goes to order of billions. So you have a binary representation of these billions, and it doesn't matter what does it mean. But when you're feeding this to the network, when you're expecting to see similar things, in principle, the idea is that this middle layer is like a compressing channel. And if there are like 2 similar words that they have completely similar surroundings, they get similar activation in principle in this layer. So they get the similar dense vector. So this dense vector should represent semantic and syntactical laws and rules in principle. So that's the whole idea. And then the algorithm is very simple. I think I should skip it now. I think it's too much. We can come back if you like. But in principle, the idea is that we have V unique words. Each word is one hot V dimensional vector, and then we have 2 matrices. One matrix is, for example, here, and one is here. These arrows are matrices, and then this is another one, and so on, right? So if you remember, the first vector if has this dimension of V by n, which means that the input is V dimension, the output will be n dimension, and the backward is from n to V. So you produce something, and then you want to see how good you are in terms of the final result. And then usually it takes 50 to 1,000, for example. So we read arrows as dot products, and there is an objective function that implies, given a word, the network should predict the context and vice versa. if one can write a parametric objective function, there are usually several methods to find an optimum value for it. So you need to write down an objective function that how close you were into the result, and this will be everywhere in all of the classifications. And it's similar to what we have in SOM, for example, that you need to be able to represent. And the method we are using, I just don't go to it. It's called stochastic gradient descent. But it's good to see how it works. So I will skip this part, but I will show you a visualization of this training process. This is just if you look at one step, for example. So this is your data sets. You have eats apple, eats orange, and so on. And then this is how it works. It says that when eat is coming, you should be able to tell me apple is the result. So think about this as a kind of one hot encoding. And then you have this middle layer, which is 5 dimension, and then the output should be this. And if the algorithm is not wrong, so you just say tune and in a backward way your weight vectors, or this means these two matrices, in a way that next time when you see eat, you should tell me apple. And then you do it a lot of time, like what we do here, for example. And then, for example, in this case, you will see that because it's a very unique case, it should help, for example, rice and meals together, but apparently it's not a good result. But I will show you a better result, which is very astonishing. But for example, this is the way it works. You just throw one by one these words. So you see what's happening. You don't construct this large matrix any longer, but you are interested in this dense vector. And think about it like a kind of filters or gates, right? And then you just train it in a way that similar words get similar gates. But you don't know what does this similarity means. That's the interesting part. This could be syntactical, this could be semantic, whatever. This could be any co-occurrences that they have some reasons. Right? For example, think about that these examples of this traffic network. Now we have these drivers, they're driving in the city, and then you have these cells of the city. There is a reason why this driver connecting these cells of the city together, but we don't know why. But then in this network it says these two cells are co-occurring, right? Then in principle they should get the same value. So I'll skip this part. If you are interested, I can explain you what is this stochastic gradient descent. So this part is not good as well. So let me show you some interesting results. That there was a group of people who did this application, and later his name is Mikolov, and later he moved to Google, and they trained this with a large data set of 5 billion words. So they did it, and now you can even use these trained vectors. And this is a nice library called GenSim in Python that we will use it now. But to just show you how it works, is that now you can, this is what I was talking about, these semantic questions. Now it says the relationship between man to king is as woman to what, for example? What do you guess? So what happens is that it finds a queen. But the way it works is that man has a vector, king has a vector, and then you can do simply algebraic calculations between this. So you can say, for example, a vector of man minus vector of king, then you have another vector, and this vector is a vector of woman. And then if you add again the same amount of values, you get to the vector of queen. So it's just doing this kind of calculation, and then it searches which vector has the similar value to this, and it's queen. For example, you can do these things like iPhone. What is the most similar word to iPhone is iPad, for example. So in principle, it has all of this information. Now you can say USA, for example. What is this trademark? What is this? Okay. It's funny, yeah.
Trump.
Yeah, we'll do it. Yeah. Okay, let's try it. I think Trump was not there that time. I hope. Okay, it was there. When they
take the verb.
Donald Trump. So some of them are not that helpful, right?
And if you write Donald Trump.
It's Trump.
Yeah, definitely.
And underscore.
Do we?
no?
We should have underscore. Yes.
Yeah.
Donald Trump. Most similar is Trump. Yes.
McDonald's.
How do you write McDonald's?
McDonald's.
Write this.
It's AC, I think.
Just check.
No, it's not AC.
No?
MC without underscore.
Is it important if you do such a small characters?
No, I think usually you can. It depends on your dictionary. For example, if I say they all have small letters, then it's fine. If you say I separate them, that's another thing. McDonald's. Yeah, maybe we should do it like this. But these are not good examples. Yeah, or which phrase doesn't fit, for example. These are kind of logical questions. Dinner, cereal, breakfast, lunch. Cereal. You see how it works? It has no clue about what is semantic or what is logic, but it just learns to encapsulate these relationalities, and that's I would say a major step in the computational modeling, because you don't need to hard code the logic. And this has a lot. I think this is one of the best examples for definition of machine learning, because without machine learning you really need to hard code the logic. Okay, if it's this, then this is relation to this, and this is that. And see a lot of if then rules, and here you just encapsulate them, and then if you get more data, it gets better always. So that's enough for now. So you can train it here, and this data is available. You can download this data. It's a bit heavy for uploading to GitHub. I think it's not possible because it's like 5 gigabytes or something, but it's a trained network. It's a trained network, so you can get this, for example, 300 dimensional vectors, and then use it for any problem that you want. It's a similar way that nowadays we are being used this kind of trained networks for image recognition. So you can use it simply for your new data as a simple and fast system. You don't need to train it, but they might be biased as well. So you can load this data and play with that, and I will show you again with this example of movie reviews. But it's not just for natural language processing, but it can be for any application. For example, if you find this kind of questions, for example, in fashion industry, this was a good example that they did this for items of these online shops, and these items simply have a number, but these numbers goes with a lot of descriptions, right? This item has this, for example, this one has a picture, so here they don't use any information of the picture, but this was, I think, back in 2012, but now they use pictures content as well. That's not a problem. They just simply say, if the person has bought this one, it's one customer, and this is item this one, and for example there are this tag of pregnant, so then you say most similar to these two, and it gives you these items, which seems meaningless, but when you visualize them you see that it has some meaning. So this can be used as a kind of semantic recommendation systems, and as you see the final result is based on pictures, but what it learns is just based on this code of the item. So this is easily possible, and there are a lot of these kind of applications. I think this one was somehow the same. Yeah, this was more or less the same thing. You can do this kind of stuff, and I think there should be already implemented in some of these online websites that we are using. Or for example, it could be music selection considering users' playlists. So don't think about words, it could be any nodes. If you have this kind of relations between these nodes, you can make these models, because then you always have these sequences of the data. For example, you can say in Spotify I was playing this, and then this, and then this. So this is a sequence of the data. You don't need to encode the whole audio itself, but you have the tag of that. So it has a unique ID, it's like one word. So you just learn that these three goes together. If it's just one time or if it's several times. Or shopping basket and so on. And then there was a nice application called DeepWalk. And this DeepWalk, it simply says, if you don't have this data of like sequences of the data, it's fine as well, because you can generate random walks in these graphs. So think about that. For example, if you have a molecular structure, or if you have a, I don't know, architectural design, or if you have a kind of, I don't know, this simple example like floor plans, and then with this semantic informations. So you can simply think about it because it's a picture or it's a kind of graph, it's a two-dimensional, for example. As a picture, it doesn't fit to this kind of sequential thinking. But what you can do is that in any graph, you can generate a random walker, or sometimes weighted random walkers, and then just train, generate 200, for example, or 1,000 random walks with this length of, for example, 10 steps in this graph from any starting point. So what happens is that they generate somehow text from that graph, because then you have these labels in these nodes of the graph or edges depending on your problem. So you just say from room to kitchen, from kitchen to, I don't know, bathroom, from bathroom to room, and so on. This is very simple, but it can be any fixed symbols. And then you can generate a lot, and then this will solve a lot of problems in graphs, because in graph theory it's not easy to compare things. But now you can compare any graph somehow to text, and then you can you can get a lot of benefits from that. Or even you can do it for images, for example. If you have images, and then you apply some kind of deep learning to detect the objects, so you can think about these objects as a kind of co-occurrences of these objects, right? So again, you have this kind of text. So you think about it in any application. Or sentiment analysis that you will see, or consider the flow of people in city. In this case, words could be buildings, streets, neighborhoods, regions, and so on. So you can represent a city if you have a lot of data from real movement of the people, but this is completely opposite or alternative to what people do in the so-called city modeling, because they always start with semantic model of the city, so this is building and so on. Here you can just predict, and you can just represent the things without touching it directly. So if you have, I think this data is available nowadays. Example of GPS traces. These are important things. These are the random walkers. Actually, they are not random walks because they have some purposes, like this text, but we don't know what are these purposes. But we have this data, so you can represent a lot of complex things that are not possible to be represented in a rational way. So yeah, I think we discussed this before, and I think even I was thinking about this, but I didn't figure out at the end, because I wrote something like this for stock market as well. You can think about this, that you have days, you have price, and then if you categorize the price, it's like the locations of this space. Just cut the price to I don't know, 10 categories, and then you have all of these words, which are the different companies. They're moving in between, right? So you can convert this problem of a stock market if you have 10,000, for example, symbols. They are moving in this space. So if you can do it, then in principle you can find nice portfolios, for example. And then you can say, like, similar things to what we said about king and queen. You can think about these different companies. I think this should be possible, but I didn't try, but I will do it because data is available. So yeah, author, papers, network, this kind of stuff, you can easily do it. And then I will just try to go to the end, this part. I will just show you how this works. Now we have again this review picture, review data, positive, negative, unsupervised, which means there is no label. And I just show you, I mean, in principle I put it here. You can use this GenSim library, and then I train a network here. I just say, for example, number of dimensions should be, for example, 150, and it's super fast. And then now you can ask these questions for yourself. For example, if you say novel, it tells you a book, adaptation, Dickens, author, so on. If this is about, like, now movie reviews, if you have some, I don't know, keywords, I don't know, anything. I will start with good, for example. Good, decent, great, bad, cool, you know. So
Oscar.
how do you write Oscar? It's like this. Awards, nomination, Academy, Emmy. You see, it's extremely powerful, and here we don't use a large data set. It's a very small data set, in fact. And you can train it.
It gives you the neighbors of the grid. You say top 5. The top 5.
Top 5 means that it's like a KNN. Each of these word, like each of Oscar now has a vector of 150 dimensions. and then it just simply looks at what are similar vectors, and it's a vector space, right? And then you say top 5, or you can say top, let's say top 50 award. I mean, and then I think at the end this should less related.
Probably, yeah.
Deservedly.
0.46 against 0.19. Yeah.
Yeah. And then, for example, there is one very known application for this. It's called sentiment analysis, and then sometimes another word for that is opinion mining. That, for example, you have a portal for your products, and then it's a kind of practical problem. And then you just launch this product, and then you want to know how people talk about this. What is their opinion, for example? So you just want to know that how many persons like it, how many don't like it. Or think about it that we have a lot of these digital review websites. That if you don't want to read all of them, you can write a bot that crawl all of them, and then, for example, you just say, after this sentiment analysis, this is what I'm going to tell you. It tells you what is the opinion about this product, for example. So what you need to do is that you simply need to now have a vector for the documents, because these are vectors for words, and each document is a collection of words. And a very simple way that would work is that you just sum all of them together, and then now you have one vector for all the words in one document, and it works very good. And you get, for example, for this case of data set, it gives you up to, I don't know, 90% quality of prediction. So I just cut these parts because I previously had this part. And the other idea would be to use, as I told you before, to use a self-organizing map to train a sum of these words, and then train another, and then project all of these documents to this word space. I will show you in a second, to represent the words, the document. Sorry. So, for example, let me show you something. Oops. This was the application that we wrote. That, for example, here it's going to. I will show you why. So in this application that I worked like 2 years ago, is that in principle, the idea is that now it goes to Twitter, it reads around 10,000 news, and it collects them like this text, and then implements this idea that what we explained, and then another steps, and then create clusters of news for you, for example. Then in principle, this news should be around some topic. So it gives you, it takes time, but I can show you, I can give you the link, you can train it. That at the end it tells you what are the topics at the moment in Twitter, for example, based on what you are following. For example, here I'm following like 100 major news agencies, financial news agencies, right? So I'm just collecting their data, and I implement this idea, and I just want to create my own newspaper. And then on top of that, for example, you can train it in a way that say, okay, I don't like this, I don't like that. So nobody knows what you're liking or disliking, but internally you can say, this is the topic that I like, because they're all vectors, right? Then you have a kind of representation for a cluster, and then you can train another classifier on top of that, which is your interest. So think about the generic newspaper nowadays we have, because if I just see the title of the newspaper that you're reading every day, I know what you're reading. But with this system, we can generate the things that nobody knows what you're reading, because now with this machine learning, you have the capacity to digest 10,000 news, for example. So just one example is that for this, this Dennis is data from Dennis. For example, for this for this IMDb data set, I just simply trained, as I showed you, I simply trained a simple vector base like this, and then train a self-organizing map. And here I just visualize it. So it's nothing interesting yet. So here, these are the words: son, brother.
Every dot is a
it's
word.
a word. Brother, friends, partner, and then let's say somewhere else.
So you're working with conceptual distinctions. Like
Yes.
these agglomerations are cells,
Nap.
or is a concept.
Yeah, exactly.
Yeah.
So column, I don't know. Some of them might be meaningless, for example, for us. We don't know, but they are somehow related. And then you take this, if you remember, you can take this as a kind of representation. Now I have a new document. I can project it in this space, and it can tell me which areas of this map got activated because of the similarity. And then you can think about this as a vector of the document. And then take this and train another SOM, for example. And then this will be, for example, you call it document map. This is the idea comes from a method, algorithm implemented in 1996 by the group of Co-Occurrence. It's called a web SOM. And that time it was really good. But now it's easy to implement it. Now again, everything is unsupervised. So there, you see the color is red is negative and green is positive. And here we don't use any kind of supervised training, but you see that it has this already embedded. You see it has this pattern from this red, and then it goes to this, and they are completely opposite to each other. And now if you have several emerging topics, you will have several topics like that, right? So yeah, if you like, you can read. What is this? I don't know. I never read them. Okay. So I did the same thing, but here is a simulation. I search for the keyword Apple in Google News, and I get around 100 news. I implemented these 2 steps, and then I visualize it like this, which is definitely not a good user interface. But then here, for example, it says, why Tim Cook is confident about Apple's performance in China. This is the title of the news. If you click, I believe it should go to the original news. So this was in back September 2016, I guess, or I don't know, 15 maybe. And then here it says, Apple CEO comments as shares plunge. Again, you see they are the same topic. Tim Cook's unprecedented letter don't help Apple from closing. And then when you move, it creates kind of map of this news about Apple's of the day. So you can do it every day. And then here, for example, Apple fast closing on wearable devices, for example. This is about, again, I think new estimate, Apple shipped 3.6 million watches, for example. These are all, again, this is about wearable device, watches, and so on. And I think if you go to different fields, this will be different. So the idea here is that, in principle, you can generate these models in a very friendly way for yourself. And this could be, for example, we didn't push it, but the idea was to develop it as like a box that generates your daily news, for example. So there are a lot of other applications that you can do, but I didn't have a result yet. For example, now I'm crawling data, I'm reading news. Actually, I'm every day I'm reading the Twitter data from, not every day, continuously, from all of this $, anything, for example, $gold, oil, a lot of different materials. So every day you have this data, and then the question is that what is the goal for that? Is that you have the price, for example. So the idea is that, I mean, if anybody is interested, I have this data now for 2 years. Yes, yeah. But I didn't manage to implement it yet. So you have every day a news, and think about it. There are a lot of people who are really reading this, like every day, just listening to the news or reading the news and so on. But what we need to do, if this is a hypothesis, I don't know if it works, you simply take these blocks of the day, whatever is the text of the day about this $ something oil, and then just learn this, and then learn this in correlation with the price, because you can get the daily price, or if you have a high frequency market, you can get the value. And then you can train whatever is inside. You don't need to know what is the reason for that, but you can learn if there is a kind of causality. You can learn if the news is this, then the price will go up tomorrow. And it's totally different than using this kind of time series forecasting. It's not time series forecasting. You just want to learn the correlation between this text and for example, what you are interested in, which is your target. In this case is the price. It could be some kind of catastrophic things. It could be some news about some famous companies and so on. You want to know if somebody is leaking some information, that there will be some changes, or they will increase the number of stocks, or this kind of things. So I just want to finish here by going back to this simple diagram, which is, I think, very helpful. Here is interesting point, because in all of this application you simply started to say, okay, I don't want to know why, but I want to know everything. So this is in the model, and that's the reason why it's kind of self-referential and then all connected. And I think you will see that in many of applications that works very well, in different fields you have these assumptions. That I think then I would just say that this is the shift from here to here. You have this shift in machine learning, and this is the engineering systems that you need to know what are you sensing, what are your actuators and so on. And here you don't know anything in principle, which looks scary, but you know actually, right? So, and if you remember, at the end, one interesting point is that when we have this dense vector, we are going back again to this. So it's really helpful at the same time, right? When you have 200-dimensional vectors, you have these kind of formats of representation, but the difference is that these vectors, which are some kind of latent space, are meaningless. Whereas in the classical modeling approach, you need to know what are the meanings. And because of that, they become complicated or complex, for example. Yeah, I think I'm done. So there are a lot of extensions of these methods. If you are interested, you can find them. Yeah, if you have any interest in any of these applications, like I think these data from food recipes are available. This data from chemical compounds are available. Text, of course, is available. And architectural data, I think, should be available. Think about now we have 17 million building in OpenStreetMaps, complete data, semantic information. So it tells you that how you can extrude the geometry of the building. So you have a lot of text in principle. So if you can write a parser, you can generate all of these random walkers or something like that. But this is just one way. Of course, there should be other ways as well to think about this geometry itself. But if you want to use these methods, you have a lot of data for buildings, for example. Then you can ask different questions. If, for example, there is a similarity between buildings, I don't know, this is very silly, in Switzerland to, I don't know, USA, I think, this kind of thing. I think you are doing this, for example, by pictures now. But they are all possible. And then these methods are so generic. It's always up to you what you're asking. Yeah. Mm-hmm. Okay.
Thank you.
Thank you.